In this video, we're going to look at how to prove the following trigonometric identities using a combination of binomial expansion and De Moivre's theorem. We're going to begin by considering the expansion of cos theta plus I sine theta cubed. We can expand this using binomial expansion. And when we use binomial expansion, cos theta plus I sine theta cubed expands to cos cubed theta plus 3 cos squared theta times I sine theta plus 3 cos theta times I sine theta all squared, and the last term plus I sine theta all cubed. We're now going to simplify it. The first term, cos cubed theta, will stay the same. The second term, I'm just going to bring the I and write it out the front so that we get plus I times 3 cos squared theta sine theta. For the third term, the square applies to the I and the sine theta so that we get I squared times sine squared theta. And remember, I squared is equal to -1. So our third term reduces to minus 3 cos theta sine squared theta. And for the last term, the cube expands out to the I and the sine theta term. So we get I cubed times sine cubed theta. And remember, I cubed is equivalent to -I. So we're going to get minus I sine cubed theta. The next step now is to group the real parts and the imaginary parts together. So we're going to group cos cubed theta and minus 3 cos theta sine squared theta. That's our real part. We're also going to group the imaginary parts, I 3 cos squared theta sine theta minus I sine cubed theta. We're then going to use the trig identity to simplify the expression further. So remember, sine squared theta is equal to 1 minus cos squared theta, and cos squared theta is equal to 1 minus sine squared theta. We're then going to expand out this expression for both brackets, and our next line becomes cos cubed theta minus 3 cos theta plus 3 cos cubed theta. And the imaginary part is 3 sine theta minus 3 sine cubed theta minus sine cubed theta. We're now going to collect like terms. So the cos cubed theta and the 3 cos cubed theta will collect together. And this will give us 4 cos cubed theta minus 3 cos theta. For the imaginary part, minus 3 sine cubed theta collects with minus sine cubed theta. So we're going to get plus I 3 sine theta minus 4 sine cubed theta. And there we've got the expansion for cos theta plus I sine theta cubed being given by this expression using binomial expansion. Again, let's consider the same expression cos theta plus I sine theta all cubed. We can use De Moivre's theorem to simplify this. De Moivre's theorem states that cos theta plus I sine theta to the power of n is equal to cos n theta plus I sine n theta. So when we have cos theta plus I sine theta all cubed using De Moivre's theorem, this simplifies to cos 3 theta plus I sine 3 theta. But on the previous slide, using binomial expansion, we obtain cos theta plus I sine theta cubed as being equal to 4 cos cubed theta minus 3 cos theta plus I 3 sine theta minus 4 sine cubed theta. But because these two expressions are the same, this implies that these two expressions must also be equivalent. So our next step is to equate the real parts and the imaginary parts. And when we do that, equating the real parts, we're going to get our first result. Cos 3 theta is equal to 4 cos cubed theta minus 3 cos theta. And by equating the imaginary parts, we're going to get our second result. Sine 3 theta is equal to 3 sine theta minus 4 sine cubed theta. Now that we've proven the results for sine 3 theta and cos 3 theta, we can use those results to help us derive the identity for tan 3 theta. We're going to begin by using the fact that sine 3 theta is equal to 3 sine theta minus 4 sine cube theta, and that cos 3 theta is equal to 4 cos cube theta minus 3 cos theta, and the fact that tan theta is equal to sine theta divided by cos theta. So this means that tan 3 theta can be expressed as sine 3 theta divided by cos 3 theta. We're then going to replace the sine 3 theta with this expression and the cos 3 theta with this expression, giving us tan 3 theta being equivalent to 3 sine theta minus 4 sine cube theta, all divided by 4 cos cube theta minus 3 cos theta. But because the expression we're trying to get to is expressed all in terms of tan theta, we're going to divide top and bottom by cos cube theta. This is equivalent to dividing every single term on the top by cos cube theta and every single term on the bottom by cos cube theta. And again, we're going to use this identity to help us simplify this expression, leaving us with 3 tan theta divided by cos squared theta for the first term. The second term, sine cube theta divided by cos cube theta, becomes tan cube theta. The cos cube theta here cancels out top and bottom, so we just get 4. And for the last term, we can only cancel out 1 cos theta, so we're still going to have cos squared theta on the bottom. And we're going to make use of the fact that 1 divided by cos squared theta is equal to sec squared theta. And we can now rewrite this expression as 3 tan theta sec squared theta minus 4 tan cube theta, all divided by 4 minus 3 sec squared theta. And one last identity, which is sec squared theta is equal to 1 plus tan squared theta. And this will give us 3 tan theta times 1 plus tan squared theta minus 4 tan cube theta, all over 4 minus 3 times 1 plus tan squared theta. So now we've got all our expressions in terms of tan, and expanding this out, we're going to get 3 tan theta plus 3 tan cube theta minus 4 tan cube theta, all divided by 4 minus 3 tan squared theta. And last step, collecting like terms, we're going to get the final result of tan 3 theta being equivalent to 3 tan theta minus tan cube theta, all divided by 1 minus 3 tan squared theta. In summary, in this video we have shown how to prove these 3 trigonometric identities using a combination of binomial expansion, de Moivre's theorem, and trigonometric identities. Thanks again everyone for watching the video. I hope you guys found that useful. For more videos on this topic or other topics, please do check out our channel. And if you haven't already, don't forget to subscribe. We do release videos weekly, and we would love to see you all in the next one. Bye for now.